So this lesson is going to be on solutions, so the different types and their solubility and how they are formed. So solutions are formed through a solute and a solvent. The solute is what is being dissolved. The solvent is what is doing the dissolving. So if you think of those little Powerade packets that you can get, the Powerade would be the solute, and you dissolve it in water, so water would be the solvent. Water is a universal solvent, so if you have water with something, that is always going to be a solvent. You cannot dissolve water. If you have water, add it to water, you just get more water. So water is always the solvent. Solutions are homogeneous mixtures. They can either be in the solid, liquid, or gas form. So things like salt water, sweet tea, homogeneous, it looks the same all the way through. So once you mix your sugar into your tea, as long as it's all dissolved based on its temperature, then you won't really be able to see the sugar in the tea. You'll be able to taste it, it's there, but those molecules are going to intermingle. With a suspension, you're going to have the particles that can actually settle out of the solution if you let it stand. Suspension is going to have much larger particles than a solution. They're going to be heterogeneous, so you could actually see those particles inside of the suspension, which means that they can be filtered. So something like muddy water, some antibiotics, you have to shake well before you administer them, and that's because those some of those particles are really large, and you got to shake them up and make sure they're dispersed throughout the mixture. Next are colloids. Colloids kind of fall in between a suspension and a solution. They are heterogeneous, but the particle size is not quite as large as a suspension and not as small as a real solution. Those particles instead are kind of dispersed, so they almost just hang in the mixture that's there. You cannot filter them out, and they will not settle out. They do exhibit the Tyndall effect, so they're going to scatter that light in all directions. You can almost think of fog as a colloid. It's water particles kind of suspended in air. So those particles are dispersed throughout the air wherever the fog is, and it's going to scatter your light. Some other examples, whipped cream. So you have a gas that's dispersed inside of a liquid. Milk, a liquid's dispersed inside of a liquid. So milk, you have those fatty particles that are in the liquid form, and then there's water in there as well. An aerosol, so you have a liquid that's dispersed in a gas. When you push it down, those liquid particles remain suspended in the gas that's propelling it, so that's kind of like a fog. Smoke, you have solid dispersed in a gas, so those solid particles are coming up off of whatever is burning, and it's caught in the gases around where the fire is. Blood is going to be a solid dispersed in a liquid, so you have some proteins, your cells inside of the liquid there. So those are some other examples of a colloid. Solubility is going to be how much of that solute can you dissolve in a given quantity of solvent at a specific temperature to produce a saturated solution. Our unit is usually going to be grams of solute per 100 grams of solvent. So how much sugar can you dissolve in a cup of water at room temperature? And that's going to be the solubility of sugar at room temperature. So 3 factors are going to affect our rate of dissolving. The first one is agitation. So dissolving is going to take place at the surface. If you take a bunch of sugar, pour it in a glass, you can almost see the sugar dissolving right at the meeting point of the liquid and the solid. It looks kind of wavy, almost like heat on a hot day. And by agitating, you're going to move those dissolved particles out of the way so that more of that solute can be dissolved. Temperature. We know if you increase the temperature, you're going to increase the kinetic energy. Those particles are going to start moving around a lot. There's going to be more collisions, So those solute particles are going to be running into the solvent particles and kind of breaking them apart, causing them to dissolve. And then size. If you have a small particle, remember there's a lot more surface area there, more collisions, so it's going to dissolve faster. A saturated solution is going to have the maximum amount of solute at a constant temperature. If you add any more solute at that temperature, it will not dissolve. So if you have a cup of slightly warm water and you start adding sugar, you're going to get to the point where the sugar's not going to dissolve anymore. It's just going to be setting at the bottom, and you have reached the saturation point for the sugar at that temperature. Now, you can make it super saturated by increasing the temperature and forcing more of the solute to dissolve. So when you make rock candy, for example, you are making a super saturated solution. You're heating that sugar-water mixture up so that more sugar can dissolve. If you have an unsaturated solution, it just means that you have less solute than it can hold. So if you have a thing of boiling water and you just add a few sprinkles of sugar, that is an unsaturated solution. You could still add more. So we need to keep in mind, like dissolves like. If two liquids can dissolve in each other, they are miscible. Both your solute and solvent will either be polar or nonpolar. So for example, water and vinegar, both of these things are going to be polar, so they can dissolve in each other. Two liquids that are insoluble are going to be immiscible. One would be polar, the other is nonpolar. So the easiest one here is water and oil. Water being polar, oil is going to be nonpolar, so they can't mix. There's not going to be any intermingling there. For gases, gas solubility is going to be affected by pressure. So I want you to keep in mind a bottle of soda, or a can of soda for that matter, for this example. Solubility is going to increase as the partial pressure of the gas above the solution increases. So those cans and those bottles are going to be sealed under pressure, and that's going to keep the gases dissolved in the liquid so that when you get your soda, it tastes bubbly. Solubility is also going to be greater in cold water than in hot water. If you've ever refrigerated a 20 ounce or even a 2 liter soda, when you take that first sip, it's extra bubbly. That's because the gases are dissolved better, so the pressure is going to be greater when it comes out, and it's going to feel more bubbly in your mouth. If you leave a soda sitting out on a warm day, it's going to go flat kind of quick. Those gases are going to escape, and your soda's not going to be as bubbly. Solubility curve. So this is a solubility curve. Down here on our x-axis, we have temperature, and over here on our y-axis, we have the solubility. Notice it's in grams per 100 grams of water. So this is saying that at 10 degrees Celsius, you can have about 20 grams of salt, of the potassium nitrate, dissolve in 100 grams of water. So you'll notice that for the most part, as you increase the temperature, the solubilities of these salts will increase. But that doesn't apply to all salts. Sometimes they dissolve better in colder water than in hot water. So make sure you understand how to read this graph. Make sure that you know, for example, here the sodium chloride, sodium chloride, you can dissolve almost 40, so about 37 grams of sodium chloride in 70 degrees Celsius water, in 100 grams of that water. So if you had 200 grams of water, then you can dissolve twice as much of that salt. So by doubling your amount of solvent, you can double the amount of solute that could dissolve.